Hello, in this video I'm going to tackle the problem that's been dogging us for the last couple of videos, and this is the problem of stellar distances. As we've been saying, if you go and look at stars in the night sky, well, some of them appear to be brighter than others, but we don't know just by looking at them whether they appear brighter just because they're closer. Unless we know the distances to these stars, we can't say which ones are actually the brightest. All we can say is which ones appear to be the brightest. And we've seen this in the analysis that we've done so far. So when we run the starlight through the diffraction grating and we're getting our stellar spectra out of these, if we look at a spectrum of a particular star, then of course we have the displacement law, which is telling us something about the temperature of the star. So that's good that we're getting information about the temperature. And that's what's then reflected in our one part of our stellar classification. Our one big apple flattens a giant killer monkey. So we're getting one part of our stellar classification. But then when it comes to Stefan's law and we're looking at our luminosity, well, that's great that we've got the temperature bit in there, but we don't know about the size of the star, the radius that we've got here, and the luminosity depends upon the distance. So we're not there yet to really say what type of star we've got. This is feeding into, the Roman numerals that we've put in the stellar classification. Are we looking at a supergiant or are we looking at a dwarf or a subdwarf? What are we actually looking at here? This is going to feed into the radius of the star. Now, these stars are so far away, we can't start measuring the radius of the star. They all just look like points in the sky. It's far too far away to actually measure any kind of extent to the star. So if we can get the distance to the star, that will allow us to calculate the actual luminosity of the star, not just the apparent brightness. And then that will tell us about the size of the star. So stellar distances are really, really important just to finish this chain of description that we've got about these stars. But this is no mean feat in order to work out how far things away, how far they are away. I mean, it's fine if you've got things that are relatively close. Like if we're just inside the solar system, there's a lot of relative motion between all of the objects. We can do a bit of mechanics and see how things are moving around. We've got lots of measurements that we can take. We can do radar ranging off of planets and things like that, bounce something off of Venus and see how long it takes for the electromagnetic wave to get there and back. So there's a lot of stuff that you can do in the solar system to get really accurate distances. The further away you get, the more problem you've got. So what are the techniques that people use? The first one that I'm going to look at is parallax. And this is still where we're close enough to an object that we can measure changes in position. So parallax is taking advantage of the motion of the Earth around the sun. So say we've got the orbit here of the Earth around the sun, and we've got two extremes, 6 months apart here. So we're on one side of the orbit over here on the left, and then 6 months later we're in the other part of the orbit. If we've got a relatively close star, so let's take something like Alpha Centauri, so say this is our Alpha Centauri, and then we've got all of our very distant stars in the background, then the position of Alpha Centauri is going to appear to change depending on what part of the year it is. So I mean, this is greatly exaggerated in terms of the distances, because of course I've squashed it in this vertical direction relative to the orbit of the Earth. So yeah, that's exaggerating things. But you can see line of sight here is putting Alpha Centauri, over here, and at the other part of the year, it's putting it over here. So for close stars, you can see this change in position relative to background stars. And we then get a distance definition off of this. So if we take the angle here, so half of that full angle, so some angle there, if that is 1 second of arc, so 1 second of arc, if we take a whole circle, So we're used to dividing that up into 360 degrees. Then we can divide each degree into, so 1 degree goes into 60 minutes, and then 1 minute, surprise, surprise, goes into 60 seconds. So we're taking a circle, dividing that into 360 to get degrees, dividing it by another 60 to get it into minutes. So let's do this as a fraction. So 1 over 360, that gives us degrees. Then we're going to multiply by 1 over 60 to get it into minutes. And then we're going to multiply it by 1 over 60 in order to get it into seconds. So this is a small angle. If we're doing this in radians, then we got 2 pi divided by all of this is going to give us 1 second of arc. So that's an angle. And if we've got 1 second of arc, then we say that the distance is 1 parsec. So 1 parallax arc second is just reduced into this name here, parsec parallax arc second. So you can do this for, as I say, for close stars. I mean, Alpha Centauri there, then you look at this, comes out at 1.3 parsecs being the distance there. So you've got an angle, a parallax angle here, which is less than 1 second of arc, which means it's further than 1 parsec away. Because as this angle gets smaller and smaller, then the object is obviously getting further and further away from the Earth. So that's what we've got for Alpha Centauri. I mean, another way of measuring distance as well, I might as well bring it in now, is light years. So this is the distance traveled by light in 1 year. So we've got our speed of light, about 3 times 10 to the 8 meters per second. Well, if we multiply it by the number of seconds in a year, we get a distance that light would have traveled. It comes out at about 9.5 times 10 to the 15 meters. So that is a light year. And a light year is around about, well, parsec is longer than a light year. A parsec is about 1 parsec. You're looking at 3.26 light years there, you know, give or take. So we've got these 2 measures of distance that we use on an astronomical scale here. If we've gone outside the solar system, you know, all the discussion we've had when we talk about inside the solar system, when we're looking at these shorter distances, these are quite often given in terms of the average distance from the Earth to the Sun. You know, so we're talking about astronomical units. So 1 astronomical unit is the average distance from the Earth to the Sun. Well, a parsec is way, way, way greater than an astronomical unit. I mean, it's over 200,000 astronomical units. I think it's 206,000 and bits astronomical units in 1 parsec. So yeah, there's a massive increase here in the scale of measurement that we're using. But I mean, this is fine for parallax, but it doesn't take you very far. By the time you've got to, you know, 100 light years, you know, 30 parsecs or something like that, you're really hitting the limit on this, because we just can't measure the angles. It is too inaccurate. They're just far too small, these angles. You can see how small an angle we're already getting down to with 1 second of arc. So once we've taken something 30 parsecs away, I mean, this is a tiny, tiny angle. So that's fine though for local stars. You know, it's made a start on where we're going with things. But we need then another measure to take us another step further away from the Earth. So taking us another step further away in these stellar distances, we've got these objects, these stars called Cepheid or Cepheid variables. I hear it pronounced both ways. And these turn out to be very, very luminous stars. Of course, people didn't know this when they were first looking at them, but it turns out they are. And their brightness varies in a periodic fashion. So there was this lady in the early 20th century, Henrietta Leavitt, I'm not too sure how to pronounce her surname, and she was observing a particular star that had this periodic change in its brightness. So it was going up and down like this, where you've got your brightness on the y-axis here, and then you've got the period of variation, so you've got time on the x-axis. And I think the first one that she was looking at was varying every sort of 5 days, something like that, between maxima. And these Cepheid variables, they have a range of periods. It can be anything from sort of 1 to 100 days. And it was found that if you plot these out, so this is on a non-linear pair of axes we've got here. So this is the number of days going along the x-axis here. So we've got 3, 10, 30, 100. You can see that's non-linear. There was this relationship between the period of variability and the luminosity. And it turns out that this luminosity, when I put the circle with a dot next to it, so L on its own would just be the luminosity. If you've got the circle with the dot, that means this is the luminosity of the sun. So it'd be a scale compared to, this is the unit we're measuring things in, how many solar luminosities. So let's say 1,000 down here. I told you these are pretty luminous things. And then 3,000, 10,000. So a similar sort of scale, non-linear scale that we've got here. And you get this straight line relationship between the luminosity and the period of oscillation. Of course, this does beg the question of, well, how did we find out the luminosity, seeing as this is what we're trying to nail down by working out these distances. But if you've managed to get some of these Cepheid variables where you have managed to pin down the luminosity because you've got their distance through other means, through other ways of working out distances, then you can start using those standard Cepheid variables. You can use those for comparison with the other Cepheid variables and then fit them to this relationship. So it certainly helps. I mean, these are a great way of getting longer distances. We're going up to now, you can get to other galaxies with these stars are so bright, so you might get up to 30 megaparsecs, something like that, at the top end, and that's a great way of getting a lot of distance information for a lot of objects, providing you can do that first calibration, which is always an issue with these things, and I'll come back to that at the end with the problem of calibrating these things. But that's our Cepheid variables. Has taken us a lot further now, up to 30 megaparsecs. Another one that's a common way of doing long distance stellar distances are these type 1a supernovae. So I know we haven't actually got on to exactly what a supernova is because we haven't got onto the life cycle of stars yet, but you've probably heard of them, and I expect you've got an idea of what they're about. This is a star that's essentially exploding at the end of its life, and it goes very, very bright in the sky because it's letting out a huge burst of energy in its sort of death throes of actually fusing material in the core and creating energy. Now, type 1a supernovae are a particular type where you've got a binary star, and so you might have you've got one star which is passing matter onto a white dwarf. So you've got a small star, the white dwarf, which is a sort of old star that's had its time in the past, and it's stopped doing fusion. You're looking at a hot core with residual energy coming out of it. This is what's left over of an old star, but it's matter gets accreted onto this star from a larger binary brother star, and this build up of matter on there, the white dwarf gets more and more and more massive until it gets to a particular mass around about 1.4 times the mass of the sun, and then it goes supernova. So it's all of this extra mass that's going on there. It then makes the star contract under the force due to gravity, and this kicks off a big energy surge as you get this chain of fusion reactions just kicking off, and an enormous amount of energy just gets thrown out. Now, the useful thing about this is when you see a type 1a supernova, then they all have characteristic light curves. So you get this same explosion of brightness as it goes supernova, and then the light drops off. Then the brightness of the star will drop off in the same pattern everywhere because they're all at this same mass. You know, if there's a type 1 supernova, that, well, this was the mass of the star, it's happening under the same conditions. So you can use these light curves and say, well, we know how bright this thing is going to be, but we know how much energy is coming out. So what height is our curve at? You know, is it something which is down here, in which case it's a long, long way away? Or is it something which is up here, which means it's quite close? But the shape of all these curves is going to be the same. So it gives us a gauge on how far away it is, because it gives us that link between apparent luminosity and actual luminosity, because the actual luminosity is the same for all of them. So that gives us a way to calibrate. And because these supernovae are very bright, so now we're getting up to, say, 10 gigaparsecs. We're getting a long, long way away. Trouble is, you've got to wait for one to happen. You can't just say, oh, I'm going to go out today and find myself a type 1a supernova. These happen when they happen, and you have to spot them, and you have to be there quickly in order to be able to get the really interesting information at the start of this light curve. If you're not catching the peak, well, you've got a problem. If you're only looking at it on the way down, well, which bit on the way down are you looking at? So you need to be on the ball to spot these things. But if you do, then they're very useful. So this is already taking us a long way away in terms of stellar distances. But as I've already alluded to with, well, how do we get these luminosities here for the Cepheid variables? There are problems still with all of this. And you can see that even now, let's go back to favourite star Betelgeuse that we keep on talking about. You look at this and you say, well, how far away is it? And you look it up and it will tell you something along the lines of, I don't know, 500 light years plus or minus 100. I mean, we're still not in any way getting high accuracy on every object in the sky, even things as well studied as Betelgeuse. You've got these big variations in how far away they could actually be. And the problems that you got in this are, so there's the obvious one of, well, how do you calibrate the first ones? Okay, it's great if you can build these things up and you can do stuff with parallax in order to say how far away something is. That's good. So we do our parallax measurements, and that gives us a lot of information about local stars. Now, it's great if one of those local stars happens to fit a particular type of star, but these Cepheid variables and these type 1a supernovae, we're not getting those in the local vicinity. These are things that are much further away. So you have to sort of build up through a process of evidence, elimination, deduction, looking at stellar spectra, trying to compare these and building up this ladder. If we can say, okay, well, we've got a fairly accurate local measurement here for, I don't know, an F-type star, maybe, let's say that, or a B-type star, then, well, perhaps that's going to allow us to build, if we see a spectrum of another F-star, which is further away, that we can't do parallax on, well, maybe we can use spectral properties in order to give us an idea of how far away that is. We might find some stars that are obviously connected to each other. We might get some binary stars or star clusters. If you've got a cluster of stars, like Pleiades or something like that, you say, okay, these are formed in the same place. We know they're a similar distance. So that allows us to group these things together. So you're trying to piece these things together in the best sort of, deductive way that you can. And then once you start getting some luminosities that you're feeling fairly confident with, you can then start expanding it to more objects of the same class. So you've got that problem of calibrating. The other problem that you've got is making sure that you're actually identifying objects that are in that class, and you're not mistaking an object for, say, a Cepheid variable when actually it isn't. Maybe it looks like one in a lot of ways, but maybe it's some other type of variable star. And this gets more difficult with increasing distance because we're getting less information from the star, we're getting less light from the star, so it can be harder to tell. We've got more uncertainty in our measurements. And this isn't just a theoretical thing. I mean, in the 1950s, they did have this exact problem with Cepheid variables. when someone spotted there's actually two different types of Cepheid variable, depending, and they vary depending on makeup. So you get some of them have got a lot more heavy elements in. They're a lot sort of older in their content. You know, this is material which has been produced over a much longer period of time. So you get these two different types of Cepheid variables, and they vary in different ways. So it turned out that actually their measurements of distance were completely wrong for a lot of variables, these Cepheid variables, and they were actually much further away than people thought. And it's actually led to the diameter of the Milky Way being doubled pretty much overnight on the realization that these distance measurements had gone wrong. So if you're doubling the diameter of the Milky Way, that's then going to have 8 times the volume. So that, I mean, that's a big change that happened only 70 years ago, where we said, well, actually, the Milky Way is 8 times bigger. The universe is then getting so much bigger as well because everything seems so much further away. Then you've got to start changing all of what you think about, you know, all your other models about the size of the universe and everything else. I mean, what if we found out a similar thing with type 1a supernovae? I mean, as far as we know at the moment, they're all exactly the same. But if someone suddenly realizes, you know what, these ones that are all the way over there are slightly different to the ones that we've been looking at more locally, then we're going to have to change all of our distance measurements again. So there's always a danger of miscategorizing something. So this is by no means a done deal, all of this stuff with stellar distances. And the further away you go, as I say, there's more uncertainty. You know, there are other methods that get used. You know, on the cosmic scale, we're going all the way up to, you know, things like Hubble's law that we're going to talk about when we're looking at cosmology. You get various things from gamma ray bursts and stuff like that. You get more and more exotic stuff which is happening further away, used as a distance guide. But again, maybe we're describing them wrong. Who knows? So this is fertile ground for astronomers. But at a basic level, we've got a reasonable degree of confidence to distances to objects, at least within our own galaxy, and to some local galaxies. So we've got a, you know, decent sort of distance ladder going on. But, you know, as I said before, we've still got fairly large errors on those. But it's enough at least to get us towards working out these luminosities. So we can calculate these luminosities now. We can go back to working out if this is our apparent luminosity, bright star in the sky. This is how far away we think it is. This will then give us a actual luminosity rather than just apparent luminosity. And then we can plug that into things like Stefan's law, and it will tell us things about the size of the star. So this is the what we're going to combine with our temperature. We're going to take luminosity and temperature, and we're going to combine those into the Hertzsprung-Russell diagram, and that is going to unlock the door to stellar evolution. So we need that combination of luminosity and temperature, which, as I say, depends on this stellar distance scale. So we're nearly there. We're nearly at the point of being able to go over to the Hertzsprung-Russell diagram. I just want to do one more thing before we get to that, and that's clarify how these luminosities and brightnesses are described, you know, by looking at things like the, you know, magnitude of the star. So this is just to get our terminology down, looking at magnitude, absolute magnitude, bolometric magnitude, things like that. And then once we've got that in, we've got all of the pieces that we need to pull together into this Hertzsprung-Russell diagram and then move into stellar evolution.